In this talk, I will discuss how we can trust modern technology, especially when technology is involved in our everyday actions. I'll start by explaining the theory behind the discussion. Next, I'll share a real-life example of a technology with unpredictable issues that made people question if they could trust it. Don't worry if it sounds complicated, I'll focus on the main takeaways from this story. Lastly, I'll dive into the reason for trusting technological systems and show how this logic builds on the technology acting in ways we expect and understand. Over the last 20 years, artificial intelligence has changed a lot. What was once a small part of computer science is now everywhere, from high-tech systems to our daily apps and games. But as AI is used increasingly, people ask, can we trust it? There's always a risk when AI helps make choices or decisions that impact us. So researchers are now studying how to make AI trustworthy. They want to make sure it's fair, accountable, and transparent. While trust in technology might seem new to computer science, people have studied it for a long time in other areas. Ethnomethodology, introduced by Harold Garfinkel, is a way of studying human interactions. In one of his early works, Garfinkel talked about how trust is crucial for making sense of everyday life. While trust has always been a topic of interest, Garfinkel viewed it differently. He believed that trust wasn't just about believing in someone or something. Instead, it was about showing that you know what you're doing. Imagine this. Trust isn't always something that we talk about openly. But when trust issues pop up, it often means there's a misunderstanding. Trust is like the foundation of a house. It's what holds everything together. Without it, our daily interactions would be unstable. This idea means that for things to run smoothly, everyone involved should believe in and constantly show that they are reliable. It's like when you're in a team. Everyone must believe that each member knows their part and can do it well. This mutual belief for trust makes everything work seamlessly. Now, this doesn't mean that we have to trust someone completely, knowing everything about their life. And instead, it's about trusting that they're good at their work. And think about it. In today's world, we often work with people we don't know personally. Whether in business, on the road, or even during medical procedures, we trust strangers based on their skills and role. But how do we know someone is trustworthy? According to Garfinkel, it's all about competence. People need to show they're good at what they do. Just saying you're an expert isn't enough. You must prove it. And if you can't, people might not trust you and you might find yourself left out. In simple terms, trust is like a two-way street. It's not just about believing in someone, but also about proving you're reliable. And in our modern world, where we often interact with strangers, this idea of trust is more important than ever. Garfinkel devised an exciting way to study how trust and understanding work in daily interactions. He called it breaching experiments. The concept is relatively straightforward. Intentionally break a silent rule when interacting with others and see how they react. For example, imagine asking someone the meaning of a super common word like table. This might sound silly, but doing so can cause surprising reactions. People might feel confused, anxious, or even guilty, wondering why you'd ask something so obvious. While these experiments made a big impact, they were often misunderstood. Some thought Garfinkel was just playing pranks or being mischievous. But that wasn't the case. He used these experiments as a teaching tool and later called them tutorials. Another sociologist, Rod Watson, called them interventions and highlighted their serious purpose. These experiments were designed to bring attention to the things we often overlook or take for granted, like trust. By breaking these unspoken rules, we can better study and understand them. In simpler words, sometimes you have to shake things up to see what's really going on underneath. And that's precisely what the examples I'll be discussing happen to do. Now, let's dive deeper into what these experiments can reveal about our interactions with technology. I'll be diving into how we can trust advanced technological systems, specifically a medical device used in big hospitals. The case I will discuss ran machine learning experiments to check how this medical equipment worked. The main focus was to see if the radiation levels from the device were safe. While the research project didn't get answers to all their questions, the work did raise some critical concerns about how much we can trust this equipment, and about the routine operations of large organizations that rely on advanced technologies. To tell this story, I need to take you into the world of angiography. Angiography is a method doctors use to see inside our blood vessels and organs. Imagine it like a GPS for surgeons. They make a tiny cut, insert instruments, and then, using the angiographic system, they can see and guide these instruments in real time. One of the main parts of this system is a giant robotic arm, shaped like a C, which has an X-ray machine attached. When a patient lies down, this machine sends live X-ray images to a screen above, showing the surgeon where the instruments are. Now, X-rays are a double-edged sword. They're super helpful because they let doctors see inside the body, but they also emit radiation. Some radiation doesn't go straight to the target. It bounces around, potentially hitting anyone nearby. A tiny dose might not be harmful, but these doses add up over time. And here's the catch. The clearer the image, the more radiation is needed, and the higher the risk. So while doctors and technicians are trying to get the best pictures, they also have to ensure they're safe. To make things a bit safer and simpler, modern machines have built-in algorithms that help control the device. Automating some decisions reduces the chances of human error and makes the process smoother. But it also means doctors have fewer choices, placing more trust in the technology. In 2015, a group of researchers got funding for a unique study. They wanted to explore the world of hybrid operating rooms, which are special surgery rooms that combine traditional surgery with image-guided methods. Why the interest, you might ask? Well, as you have already seen, while radiation in these rooms help doctors see inside the body, it's also risky. The challenge is that handling this risk is burdensome for hospitals. Even experts who know a lot about radiation might not understand the fast-paced world of a hybrid operating room. This gap means that doctors and nurses might not always have the correct info or training about safety. So the main goals of the project were to improve safety routines, to reduce radiation risk for staff, and to explore how to make treatment safer for patients. The team was diverse. It had people who studied workplaces, communication, radiophysics, and even a surgeon who was also a radiology professor. To gather data, they used two primary sources. The first was videos from the surgeries. The second source was structured data like radiation dose rates, time, imaging system settings, etc. Next, the research team decided to focus on one kind of surgery: endovascular aortic repairs. Over 18 months, they documented 70 such surgeries, with 12 recorded on video. In the end, they had about 60 hours of footage and 27,000 data points, with info ranging from patient ideas to the exact time and radiation levels during the surgeries. What happened next then? Well, here's where things get interesting. The way the team analyzed the data was a bit like one of Garfinkel's breaching experiments. What they found from the data wasn't what they expected. And understanding these surprises can give us new insights into how much we can trust technology that uses algorithms. When the research team started analyzing their data, they found something odd. There were considerable differences in the amount of radiation used during different surgeries. Sure, surgeries can vary, but this difference was way too big, like comparing a puddle to a lake. They soon realized that these differences came down to the exam set, specific settings used on the angiographic system. Think of these sets as presets on a microwave, each designed for a specific dish. One particular setting, DSA 421, was used often. And while it was used for only half of the recorded surgeries, it accounted for 90% of the total radiation. This was puzzling, so the team dug deeper into this setting. Now, DSA stands for Digital Subtraction Angiography. It's an imaging method that takes pictures as a special dye moves through the blood vessels. Subtracting initial images from later ones removes bones and other structures, leaving only the dye-filled vessels in the picture. And the 4:2:1 part means it captures 4, 2 or 1 image every second. On paper, this setting looked consistent and predictable, but in real-life surgeries, things weren't so straightforward. Even though the setting said it would use a specific electric power, like 70 kilovolts, the actual data showed many variations. It's a bit like setting your oven to 200 degrees, but finding it sometimes heats to 150 or to 250 degrees instead. In short, while the machine's instructions seemed clear, its actual behavior was more unpredictable. This raised questions about how much doctors could trust this technology during surgeries. When analyzing their data, the researchers faced a question. Why did the radiation doses vary so much between surgeries? Some doses were much higher than others. Was it safe? And when did these differences happen? Based on fundamental physics, you'd think that radiation dose would be consistent. But there seemed to be an underlying algorithm that changed things up. It was like trying to see a pattern in a maze of mirrors. This situation is what experts call black boxing. Imagine you have a magic box, you put something in, something else comes out, but you have no idea what happens inside. This black box concept isn't new, and it's been used to describe computers for ages. Today, with the rise of AI, especially complex systems like deep neural networks, this black box issue has become a hot topic. Can we trust something if we don't understand how it works? But here's the twist. Some machine learning tools can actually help us peek inside these black boxes. And that's what the research team decided to do for the examined settings. The team turned to MATLAB, a software tool to build a model predicting radiation levels based on various parameters. Think of it as trying to guess the weather based on factors like temperature, wind, and humidity. With this model, they could visualize each surgery's actual radiation dose and compare it to what the model predicted. This visual, called the individual conditional expectation plot, showed some surprising patterns. For instance, the expected radiation dose was lower at certain electric current levels than at others. And this was puzzling. The plot revealed two distinct groups of radiation doses. Within each group, the radiation dose decreased as the electric current increased, a relationship that wasn't straightforward. It was clear there was another factor influencing the radiation levels, like a hidden hand steering the ship. In summary, while the researchers had uncovered some of the mysteries behind the radiation doses, there was still more beneath the surface, waiting to be discovered. Scientists working in labs often encounter unexpected challenges. Garfinkel had a funny name for this and called it the demonically wild contingencies. It's like trying to bake a cake for the first time and worrying that you've missed a tiny detail that will ruin everything. But the research project's variations were different. Here, they weren't dealing with an unpredictable experiment, but with a well-established medical practice, overseen by top agencies. The research team believed that the machine might have some built-in automation, causing these odd variations. But even if the machine made decisions on its own, those decisions should follow certain rules. So they set out to uncover this mysterious rulebook. The team thought the variations might be due to physical factors, like the patient's size or the gap between the X-ray source and the detector. A larger patient would mean that the X-ray would travel further, increasing the dose. But when they plotted patient's body mass index, it didn't explain the variations. Further analysis showed that the setting called focus was the main factor. Focus could be set to either small or large, and it was related to the electric current and potential. Depending on the focus, the current and potential would be in one of two ranges. So this explains some variations. But it raised another question. Who or what was deciding the focus during surgery? The document said the focus should be small, but that wasn't what was happening most of the time. Now the team had new questions. Were the operators causing these variations? Or was there a hidden algorithm making decisions that no one could grasp? To dig deeper, they looked at the video recordings to see if they could spot the moments when these odd variations occurred. They wanted to know if the surgical approach or changes in the technique played a role. But the video didn't give a clear answer. They did, however, show that even in similar situations, the machine settings changed unpredictably. While some variation is normal, seeing the machine settings change randomly was alarming. It's like driving a car that randomly speeds up or slows down without warning. This unpredictable behavior was a major concern for the team, as it could impact the safety and effectiveness of surgery. Imagine being a flight controller, managing the safe landing and takeoff of planes. You rely on technology, trusting it to function as expected, because any glitch can lead to catastrophic results. This trust in technology, as Anderson and Sharrock put it, is essential. Without it, every routine task becomes a potential crisis. For the controller, trust ensures that planes land and take off safely. If that trust is shaken, the entire system could collapse. Similarly, in our hospital setting, everyone assumed the imaging system worked as it should. While there might be minor glitches, these could be tweaked and fixed. But the research data showed something different. The concerns weren't just about the end result, but the processes and inner workings of the machine. Using machine learning, the researchers peeked inside the system, and what they found was unsettling. It's like taking your car to a mechanic, expecting a simple tune-up, only to be told that the engine's inner mechanisms are chaotic. Either the hospital wasn't controlling radiation levels properly, or there was an unknown factor that would clear up the confusion and make everything normal and under control. What the researchers faced was a disruption in their trust. Their belief in the machine's routine, reliable performance was shaken. This wasn't a minor glitch. It questioned the very foundation of their work. In any system, when there's a disruption or breach, there's an effort to fix it. It's like when a musician misses a note, the band tries to get back in tune as quickly as possible. The researchers were trying to do just that, find a way to understand the problem and restore their trust in the technology. Say you've just bought a brand new high-tech gadget. It's working mostly fine, but there's this one glitch you can't figure out. So you call in the experts, but even they are stumped. This is what happened at the hospital with this state-of-the-art imaging system. The team tried to solve the mystery internally, but hit a wall. So they reached out to the technicians responsible for the machine's setup. But these technicians, as knowledgeable as they were, suggested the issue might be above their pay grade. It seemed the people who actually built and programmed the system might need to step in. So the researchers set up a video call with the big guns, the chief technical engineer and his team from the company behind the technology. The hospital's lead investigator presented their findings, hoping for some clarity. But instead of answers, the meeting raised even more questions. The developers found some of the hospital's findings strange and unexpected. They wanted to see the full image data the machine produced to get a better sense of what was going on. There was only one problem. The hospital didn't have that full data. Due to storage procedures, they only kept reference images and some basic data. The detailed images, those got deleted as new surgeries took place. This revealed an interesting point. The hospital had never needed that level of detail before. In previous studies, they had only used summary data. Deep dives requiring the full image data, those had always been done remotely by the developers. This meant that the research project hit a dead end in terms of the data. But the whole journey, the questions raised, the mysteries uncovered, offered valuable lessons, as we'll see next. By examining this example in much detail, we have seen a series of experiments that revealed unforeseen outcomes. It's like when you're doing a regular task and suddenly something unexpected pops up, making you wonder why you hadn't noticed before. Many times in our daily routines, we overlook a lot of details simply because they don't seem relevant. Garfinkel had a name for this. He talked about the perceived normality of events. In simple terms, it's how we view things around us based on our past experiences. If something doesn't fit our understanding, we try to make it fit or understand why it's different. In order for our world to be reasonably stable and predictable, we need to deal with inconsistencies. So whenever they occur, they should be resolved. For instance, imagine you've always believed that there are only two colors, black and white. One day you come across the color blue. You'd either try to fit it into your black and white worldview, or you will have to accept the existence of a new color. And if you think that color is too trivial an example, you can exchange it for the notion of gender. Similarly, in the study, the team found results they didn't expect. They tried to make sense of these results based on what they already knew. Garfinkel believed that when we encounter something that doesn't fit our understanding, we have two main reactions. We either challenge our current beliefs or try to force the new information to fit our existing ideas. He said that true scientists are open to changing their beliefs when faced with new information. On the other hand, some people might stubbornly try to make the new information fit their old beliefs, which isn't always the best approach. Applying this idea to the study, it's a bit unfair to say that the team was being stubborn or close-minded. They were dealing with complex systems, and sometimes the data they got didn't have a clear source or explanation. If you can't recognize a piece of information, one possible interpretation is that maybe it's not addressed to you. It could be someone else's problem. Moreover, professionals like doctors can't afford to be constantly changing their methods based on every new piece of information. They need to trust the systems they use. It's like trusting the brakes of your car and that it will come to a stop whenever you need. If you can't operate on that basic assumption, you will never even enter into the car in the first place. Driving becomes impossible without this assumption. But your initial trust is also validated and reaffirmed every time the brakes function as expected. In this project, the team couldn't figure out why certain things were happening. They had theories, ideas, but nothing concrete. And in situations like this, it can be tempting to look for a scapegoat, a reason, even if it's not the real reason. This is what the concept of the ghost in the machine represents. It's the mysterious force, the unknown entity causing the unexpected events. But the real lesson from this project isn't about finding the ghost or not. It's about understanding the complexities of trust in modern technological systems. Just like we trust a car's brakes, we trust complex systems to operate as expected. But when they don't, it can shake our faith, our trust. Without trust, our ability to go on, to act, is ground to a halt. In the end, the research project didn't find all the answers, but it did shine a light on the challenges of trust in a technological age. And while we may never fully understand every ghost in every machine, we can still strive to understand the systems we rely on every day. To enable a critical reflection around trust, we should strive to better understand what our expectations are. Expectations that are not always being made explicit. And we should understand which types of confirmations from the systems work to reaffirm our trust. These are the basic mechanisms by which trust operates, regardless of whether they are warranted or not.